The last glacial period on Earth began to fade around 11,000 years ago. The kilometers-thick ice sheets that covered much of the Earth started to recede, and the Earth entered into the Holocene, the current geological epoch. But the once mighty glaciers did not disappear entirely. In the extremes of our Earth, the North and South poles are the remnants of the last ice age. These frozen tundras easily reach temperatures as low as -40 degrees Celsius, and sometimes dip far below that. Darkness envelops them for entire months at a time. They are places that seem wholly inhospitable to any living creature. Temperatures are so low that hypothermia can quickly set in, and ice itself can form inside the body, its crystals shredding tissue, ripping cells apart. But for millions of years, evolution has forged remarkable adaptations across the animal kingdom to ward off the icy grip of death. It's the reason Arctic animals have specialized heat-generating tissue, and the reason polar bears are invisible in infrared vision. It's what shaped our circulatory system, and why so many traits appear in cold weather animals that appear nowhere else in the evolutionary tree. When the ice starts to take hold, what hidden strategies, compounds, and dynamic physiologies of animals that live in these frozen tundras allow them to survive? Sub-zero temperatures are a problem for all living things, because all living things are largely made up of water, and when water freezes, it expands and becomes sharp. This is frostbite, a death sentence for any cells it forms inside. Cells that make up vital organs also have optimum operating temperatures, and when core body temperature falls, the heart, nervous system, and other organs can't work normally. This hypothermic state can lead to complete organ failure and eventually to death. And so to survive an extremely cold climate, there are two things an animal can do: prevent heat from leaving the body or create more. The animal kingdom is made up of endotherms and ectotherms, the fancy words for warm-blooded and cold-blooded animals. It's a misconception that cold-blooded animals don't create heat like warm-blooded animals. They do. They just can't retain it and regulate it like the endotherms can. Endotherms, primarily birds and mammals, use metabolic heat to maintain a stable internal temperature, often one warmer than their environment. When it gets particularly cold outside, endotherms can increase metabolic heat production in what's called thermogenesis. One of these methods is something we're all familiar with on a very cold day: shivering. Skeletal muscles tighten and relax in rapid succession to produce extra heat and keep the body warmer. But some animals, especially hibernating ones, have an extra heat-generating power. Using a specialized fat tissue called brown fat or brown adipose tissue, animals can create heat without moving a muscle. This is called non-shivering thermogenesis. Brown fat works very differently from white fat, which is the fat we're more familiar with. White fat stores extra energy and is what builds up in obesity. But brown fat breaks down sugar and white fat to create heat, burning up calories instead of storing them. Brown fat generates 300 times more heat than any other tissue in the body. It's loaded with much more mitochondria than white fat, which also act differently than most mitochondria. Rather than creating ATP, the energy-carrying molecule, like most mitochondria do, these mitochondria are designed to turn fuel molecules directly into heat. Small mammalian hibernators use brown fat more effectively than any other creature. Before hibernation, they undergo a large increase in brown fat, not to get through hibernation itself, but rather to help them get out of it. Hibernation involves going into a state of decreased physiological activity, usually paired with a reduced body temperature and metabolic rate. This decreased state of activity is called hypothermic torpor. It enables animals to survive periods of reduced food availability, like in harsh frozen winters. But when more favorable conditions arise, these animals need to be able to raise their body temperature to return to the world in search of food. And arousal from this state is no trivial task. It takes about 1 hour and involves violent shaking and muscle contractions, while brown fat works to burn off energy stores to rapidly warm the body. But creating heat like this comes at a great cost, energetically speaking. As much as 75% of the total energy expended during a torpor bout is used just for arousal. A huge amount of calories needs to be consumed for any amount of thermogenesis. And this is why sometimes it's better to not just create heat, but to keep it from escaping in the first place. The temperature of water in the Arctic Ocean hovers around -1.8 degrees Celsius. It can be at a below freezing temperature due to its salt content. Since water conducts heat 25 times more effectively than air, water this cold is capable of sapping away large amounts of body heat. But what should be an inhospitable place for mammals is instead full of them. And surprisingly, marine mammals have no special increased heat-generating mechanisms, no increased metabolism to keep them warm. Instead, they have an adaptation found nowhere else in the animal kingdom: blubber. Blubber is a specialized layer of fat that lives under the skin and is anatomically and biochemically adapted to be an efficient thermal insulator. Like other adipose tissue, blubber is composed of numerous fat cells called adipocytes, which are filled with lipids, aka fat. Blubber can be up to 93% lipid with very little water content, and because lipids have a low thermal conductivity, it doesn't transfer heat as well as other tissues like muscle or skin. This makes it an excellent insulator. Blubber covers the entire body of animals such as seals, whales, and walruses, except for their fins, flippers, and flukes. Animals with the thickest blubber, like right whales, can have blubber as much as 50 centimeters thick. Other animals, like polar bears, have up to 11 centimeters of fat surrounding them to help keep them warm in the water. But when on land, a different adaptation exists to keep them warm: their heavy fur coat. Close to their body is fluffy white fur, which traps dry, warm air next to the skin. And all around that is their outer coat, which is made up of hollow, transparent hair called guard hairs. And because of these hairs, polar bears are almost completely invisible in infrared vision. Infrared radiation is a part of the electromagnetic spectrum that we can't see but can feel as heat. Warm bodies emit this radiation, which is what infrared cameras can pick up on. Polar bear guard hairs absorb this radiation more effectively than almost any animal, hanging on to the warmth rather than letting it be lost to the cold environment. And because nearly all of the infrared radiation is absorbed, it won't show up on infrared cameras. This makes aerial surveys and population counts challenging for researchers. Their white color camouflages them, and only their nose, eyes, and breath appear in the infrared spectrum. A polar bear's specialized fur is a very effective way to trap heat against the body, but some animals aren't lucky enough to have such an effective coat, most notably us. This is why a more hidden adaptation courses through the body of many endotherms. The body's surface is the main site for heat exchange with the environment, especially in those of us with no fur. As warm blood flows to the outside of our body towards the skin, heat radiates away and is lost. And so, when the temperature outside plummets, the flow of blood to the skin has to be controlled to keep the body's core temperature at a safe level. And while hidden beneath the surface, you've probably felt this effect. Once the body senses cold, it constricts the thin web of capillaries in your extremities, starting off with your fingers and toes, then moving farther up your arms and legs. This shrinking of the blood vessels is called vasoconstriction, and its goal is to keep warm blood around the vital organs, keeping them safe, even if it means risking frostbite in the extremities. Many endotherms have this vasoconstriction ability for when the weather gets cold. But to keep their extremities from being damaged, some animals have counter-current heat exchange systems that allow heat to be transferred from blood vessels containing warmer blood to those containing cooler blood. Animals like wolves use this extensively in their legs and feet to keep them from freezing. Blood leaves the wolf's core at a warm body temperature and travels towards the feet, while the blood returning from the feet has been cooled down from the environment. As the cold blood runs up the leg from the foot and passes by the warm arteries, it picks up most of the heat from the arteries from conduction. And conversely, the blood flowing down from the body is cooled. This means that less heat will be lost from the feet due to the now reduced temperature difference between the blood and the surroundings, and that the blood moving back into the body's core has been warmed, helping maintain the body's core heat. Humans can do this to some extent, but not as well as many of the Arctic endotherms. Instead, some people, particularly people whose ancestors lived in Arctic climates, take the vasoconstriction of the blood vessels one step further. After some time in the cold, certain people's constricted capillaries will suddenly dilate, sending a rush of warm blood into the now freezing extremities, briefly warming them before constricting again. This prevents the extremities from being severely damaged by frostbite, while still ensuring that the vital organs stay warm. The cycle of constriction and dilation is called the hunter's response. People who live in cold environments, or people whose ancestors did, have this automatic response. Inuit hunters, for example, can raise the temperature of the skin in their hands from almost freezing to 10 degrees Celsius in a few minutes. Cold-tolerant animals, like those found in the polar extremes of the Earth, are at constant war with freezing temperatures. Behavioral strategies, physiological processes, and anatomical features all work together to keep the cold out of their bodies. But what if avoiding freezing wasn't the only option? What if instead, you just let the ice take you over? For us and most animals, this would mean certain death. But for some strange animals, giving in to the cold entirely is not only possible, but advantageous. Some animals even take it so far as to freeze completely solid. Their heart stops, their brain activity ceases, and yet, come spring, they completely recover from what should have been certain death. In the next video, we'll explore how scientists have realized that preventing freeze is not the only way to survive the cold, and see how we humans are trying to harness these powers for ourselves. Behind every piece of research, every scientific story, there is a human one. Much of the ecology and physiology explored in this video was only made possible by the people in the field, in these icy landscapes taking measurements or observing animal behavior. These human stories fascinate me as much as the science ones, and this is why we decided to start a podcast to explore just this. Modulus, hosted by me and Brian from Real Engineering, is a podcast about the people behind the scientific stories we tell you here on YouTube. We will talk to the scientists who are on the cutting edge of research, and the people who are affected by the topics we discuss. From people who have spent months as saturation divers at the bottom of the ocean, to the people pioneering liquid battery technology, to the people affected by the decision to introduce genetically modified mosquitoes in Florida. This podcast will show the real-life people behind these topics and the real-life impact these scientific stories have on the world. The first episode of Modulus launched today on Nebula, the streaming platform made by me and several other educational YouTube content creators. It's the place to watch and listen to our videos and podcasts ad-free, along with original content that's not available anywhere else, like Real Engineering's The Logistics of D-Day series or Tom Scott's game show Money. We can take more risks on Nebula, where we don't have to worry about the YouTube algorithm. There is so much original content there, with more being added all the time. And to make it even better, Nebula has partnered with CuriosityStream, the streaming platform with thousands of high-budget, high-quality documentaries. There are loads of documentaries about ecology and animal behavior, like this one called Polar Bears. It's a beautiful overview of polar bear biology, with stunning cinematography of the Arctic landscape. If you've hesitated before to get CuriosityStream and never quite pulled the trigger, now is definitely the time to do it. For a limited time, CuriosityStream is offering 41% off their annual plans, making a yearly subscription just $11.79. That's less than $1 per month. So by signing up at curiositystream.com/realscience, you'll get a subscription to CuriosityStream and a subscription to Nebula for just $11.79 for the entire year. Signing up is also the best way to support this channel and all of your favorite educational content creators. Thanks for watching, and if you'd like to see more from me, the links to my Instagram, Twitter, and Patreon are below.